All right, good morning, everybody. My name is Brian. I will be on stage as little as possible so that you can actually learn something. Today we're going to learn about Node.js and why exploits can stay in the wild for weeks without anybody knowing it. The person who's going to tell you about that is Jarrod Overson. Jarrod's the Director of Engineering at Shape Security. He led the development of Shape's enterprise defense. He's a frequent speaker on modern web threats and cybercrime, has been quoted by these little organizations like Forbes or the Wall Street Journal, CNET, you know, fly-by-night stuff. He's the co-author of O'Reilly's Developing Web Components. What animal is on the front of that book? A carp. Wow, we're really running out of animals for O'Reilly books. He also created Plato, which is a static analysis tool for web applications, and he frequently writes and records topics about reverse engineering and automation. Everybody, please welcome Jarrod.
Hi, everyone. Thank you very much for being patient. It's always the fun part of this. This is nailed down, and so that I'm not going to be bending the whole time, I will hold on to it, and hopefully it works. So yeah, I'm Jarrod, and I'm going to be talking about an open source supply chain attack that affected millions of developers late last November. So to get started, just to set the stage a little bit, how many people feel uncomfortable looking at instructions like this? Good. This is a security conference. It's good to see so many hands up. At other conferences, they're like, what's wrong with that? That's just normal. You copy that into your command line and you move on. This should terrify you a little bit because you're just piping whatever you get from the internet into something that interprets it into commands that your computer runs. You should feel uncomfortable. You should leap over the keyboard and stop your coworkers, or at least let them know what's going on before they enter this in. You might write blog posts about how much it really, really bothers you and how much other people shouldn't be doing this. And maybe if it really, really bothers you, you'll catalog a list of all the offenders just because that's what some people on the internet do. But now, how many people feel uncomfortable in doing this? Good. I mean, this is a security conference, and please, you really should be putting your hands up, because this is the exact same thing. You're downloading code from someplace written by somebody you don't know through the same channels that we basically browse the internet all day, and then running it on your computer, and who knows what it's going to do. Now, this is not necessarily exclusive to NPM and Node. This is basically a problem all the way around, and it is a serious problem that has manifested into real-world damage. So late last year, there was a malicious, or there was an exploit of a very, very popular NPM package that was downloaded 8 million times before it was even discovered. And this is what we're going to be going over right now. We're going to be diving into the different payloads. We're going to be talking about how it happened, what it did, and then finally where it leaves us. But first of all, why should you be listening to me at all, and why should you not be going to track A, where there might be something that is being talked about by somebody you like better? I'm Jarrod Overson, Director of Shape Security. We protect a lot of websites against large-scale automated attacks. I write a lot about reverse engineering, JavaScript, breaking web applications, stuff like that. I was an old-school video game hacker way back in the day. That's how I got interested in computers. If you ever downloaded any StarCraft or Fallout or Total Annihilation hacks, things like that, might have been some of my stuff way, way long ago. And no, I won't tell you what my handle was. You can find me at JS Overson just about everywhere. One of the things that I inevitably come across when I say that I work at Shape is a bunch of blank stares because no one knows what the hell Shape is. Shape Security is a company based in California, like all companies are. Rather than actually talking about it, I'd like to ask you first, have you ever heard of YKK? Anyone know what YKK is? There's a few hands that show up right there. Now, I guarantee you, every single one of you uses YKK daily because they make virtually all zippers that exist in the world. If you take a look right now at your crotch and look on your zipper, you'll probably see YKK on it. And if you don't, then your bag or your hoodie or whatever else. There's just zippers everywhere. Anyway, Shape is the YKK of the internet security. We use this virtually everywhere. You don't know we exist. We protect lots of login forms, AJAX requests. We're basically the reason why you're starting to see fewer CAPTCHAs and have to log in less. Super exciting stuff. But we do a ton of stuff with JavaScript, and this is what got me into a research position going through the reverse engineering of malicious JavaScript. I manage and maintain a repository of all bad JavaScript that I find because I just find it really, really fun. So first off, how it happened. Started with a package called event-stream. Actually, how many people are Nody people here? Nody, not Nudie. Very, very few. That's totally normal. In web conferences where I talk, the audience is always like, things are insecure? At security conferences, everyone looks at me and is like, people use JavaScript? Yes, JavaScript is very, 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 very popular. Easily the most popular language that people develop in nowadays just because you have to. You have to develop JavaScript in order to target the web, and Node.js is a very, very popular environment to program JavaScript in. Event-stream is a package that exists in the NPM ecosystem. NPM is the node package manager, like gem, pip, stuff like that, cpan if you're a Perly person. Event-stream was one of the first major modules that abstracted away a lot of the weirdness of Node's streams. Streams are native objects that allow you to stream data and do all sorts of magic. EventStream made that easier. Now, being an early package that abstracts away something low level in an ecosystem that expands rapidly, you will get a lot of people to depend on you very, very quickly. As of this screenshot, which was actually about a year ago now, shortly after the event, there were over 1,600 dependents. Now those are direct dependents, not even second, third, or nth tier dependents. As soon as you spiral out from there, you start to see that this package was dependent on by virtually everything. It had 1.2 million weekly downloads and was just a very, very popular package. Was maintained by a very, very popular developer, Dominic Tarr. This is not a no-name developer. This is a guy that a lot of people know, a lot of people trust, and he writes a lot of code. He has almost 3,000 followers on GitHub and just publishes code nonstop. One of those people. We all see those people, and they look like mythical code junkies that just constantly push out everything, and the entire world builds software on their backs. Now, this is someone that you should trust, right? When you're looking for packages, you look for somebody who has a long history of trustworthy code, because we're not doing any audits besides that, so that's pretty much all you got to go on. Now, September 2018, Dominic gave ownership to a user called Write9Control. Now, why would somebody give a very, very popular package to somebody they didn't know? Anyone do open source stuff here? Publish open source, contribute to open source? A lot of people probably want their packages to be used. It would be exciting to have a package as depended on as EventStream. A lot of people, when they're working on something that they're passionate about, think maybe one day you'll get 100 users or 1,000 users. 1.2 million weekly downloads is just astonishing. Why would somebody who has such a popular package just give it away? Well, luckily he told us in the issue that initially prompted a lot of discussion around this, the user just asked for it over email. And that's okay. I mean, these are open source developers. They're not getting paid. They deliver something that is useful to the world, and we can't expect them to develop it and maintain it for the end of time. Somebody else has to end up taking it over in order for it to continue. And if somebody's interested in the package and they email you it, and they look, I guess, not super shady, and even if that even crosses your mind, then you just give it to them. Not exactly the best from a security perspective, but it's just a natural way that these things are going to progress. We can't really expect a whole lot more when we're taking things for free and using them for free. So Write9Control gained trust by committing several innocent changes. This was a package that had been largely untouched for a couple years. Things like updating dependencies, updating documentation, adding some different examples, all basic stuff, normal stuff. On September 9th, 2018, Right9 Control added a new dependency and released version 3.3.6. New dependency was flatmap stream, anchored to a version 0.1.0. But let's talk about that carrot real quick. People familiar with semantic versioning? Is that semantic versioning? When I say that, is that something that's like, yeah, I know that, or like, I don't know what the hell is going on? And there was no hands for anything there. How many people have no idea what semantic versioning is? That's okay. All right, cool. Semantic versioning is a way of describing essentially a decreasing or increasing risk of a particular change. So you have a major, a minor, and a patch version embedded in the entire version string. Patch version should be things like security updates, bug fixes, something that doesn't actually affect any behavior. Minor versions should be added features. So if you update to a minor version and you're not, you shouldn't expect any changes in behavior for the stuff you're already using. A major version change is just a new API change, something breaking, incompatible. You bump them in major version. So this allows us to basically update to things with some understanding of the risk involved. Of course, it's literally just a string that anyone can change however they want. There's nothing actually hard coding these rules, so it's just up to the developer to manage that. Now, NPM has the NPM package JSON, which is where you define dependencies, descriptions, stuff like that, has a way to clamp these versions so that they will automatically update to a range that you are okay with. So if you specify a caret and you let's say clamp it to 0.1.0 with a caret, then it matches all minor and patch versions. So if you wipe away your dependencies and reinstall, you will automatically update anything that has updated the minor and patch versions. And if you use the tilde, it only does the patch versions. So it's a good way to make sure that you're staying reasonably up to date with your dependencies. But as this is a room full of security professionals, you probably already are getting a wind as to what dangers that might entail. So Right9 Control then removed flatmap stream and updated event-stream. So it removed the flatmap stream dependency and updated event-stream to version 4.0.0. This doesn't look like anything strange. Nothing malicious has actually happened yet. The Right9 Control added some features, then removed those features, and then bumped the major version. Nothing wildly strange about that. The total time between the first commit and version 4.0.0 was 12 days. Nothing malicious has happened so far. So on October 5th, 2018, is 31 days after the transition of control, flatmap stream at 0.1.1 was published. This had malicious code in it. Now, event-stream 336 installed fresh will include new versions of flatmap stream because of that caret. Event stream at 335 was stable for 2+ years. And NPM, by default, included dependencies with that caret. So basically, any project that installed event stream by default will automatically pull in this new dependency automatically, or will update to 336 next time event stream gets updated, which in turn will update flatmap stream to 0.1.1. The time between malicious control and discovery was 77 days. The time between flatmap stream 0.1.1, the malicious package, and exposure was 48 days. So there was a malicious code in the wild being downloaded by developers all around the world for 48 days. So next section here, we're going to go into what it did. It was 3 payloads, and we're going to dive through each payload and show you how this malicious exploit dug its way into an actual mobile application that could have existed on your phone. But first, we're going to talk about how it was actually discovered. Payload A, the first payload, used a method that was deprecated in Node version 11.0. So the way these things work, first deprecated methods get deprecated in documentation, then the next major version of Node deprecates them with runtime warnings, and then the major version after that removes them from the standard library. So in version 10.0.0, this method was documentation only deprecation, and then version 11.0 took it or started to warn about usage of these methods. Node version 11.0.0 was released only 18 days into the exploit. So what this meant was that completely unrelated packages started seeing warnings thrown to the console because they were using this deprecated method. This is an issue opened on an unrelated repository. This is NodeMon, which is a popular node monitoring process. It monitors scripts. We'll reload them when they change. We'll restart them if they die. Something that should be completely unrelated to cryptography deprecated methods. So once these what these warnings started popping up on the console, it understandably concerned a few people, and eventually people tracked it down to event-stream, and a user called Falling Snow opened up an issue essentially asking, WTF? There's something clearly strange going on here. Why did you transfer controller? Why did you give access to this user? What is this doing? Why did you remove it without telling anybody? What's going on? So how was it discovered? Pure dumb luck. The attacker who delivered the code into flatmap stream used a method that was deprecated, but it was not issuing any warnings at the time of development. And then when Node just naturally updated, it started throwing warnings. And if that never happened, I don't know when this would have been found. So let's dive into what this actually did. So this is what flatmap stream version 0.10 looks like. This is the non-malicious version, and if you are somewhat astute in the realm of development, it should look a little strange for you by default because it's just a bunch of code smashed up together. This is normal for the JavaScript ecosystem because of just the transpilers, compilers, bundlers, whatever else. It just smashes up code into what distributable artifact you're trying to build, and then if you try to look at it, you're just out of luck. And that's what we have grown to live with. Flatmap stream version 0.11 had this, I think it was 382 bytes added to the end of it. Looks very, very similar to the rest of the code. Nothing that should throw you off right away. But this is the code that was malicious and caused all the panic. So payload A, we're going to dive into that. This is the Bootstrap Payload. We're in the security world right now. We know how these things work. The first payload is the fun part because that is what gets your foot in the door. That is what allows you to continue the attack and then dig deeper. This is what it looked like, all prettified. We're going to smash that a little bit because there's stuff that we don't really need to care about. The first thing that you should be focusing on right now is this line right here. This is the first executed expression. This is a require of something that looks like a hexadecimal string. Require in Node.js is your import method. So you require dependencies, and whatever you're required will be imported into your script, and you can access things from there. So it looks like a hexadecimal string because it is a hexadecimal string. Once you unhex that, you see that it's requiring a file called ./test/data. So it's looking for a JavaScript file in its dependency file structure. Take a look at that, and it's just a bunch of hex strings. This file existed only for flatmap stream version 0.11. It did not exist in other versions, but it really wouldn't bother people for seeing it because it was in a test directory, and I guess people just assume test directories don't cause damage. So when you unhex those values, the first two values are very, very large. They unhex to something that some binary data. The other stuff unhexes into stuff that looks a little bit shady. And this is one of the reasons why, of course, you extract these strings and you obfuscate them, because if you were looking at a dependency update and you started to see references to AES or ciphers or cryptography, you would probably be a little bit concerned, because this is a dependency that really shouldn't be doing anything at all with cryptography. So after some replacement of those values and some cleanup of the original payload, this is what we're looking at now. So the first line that we're dealing with is just the requiring of the test data. We're throwing that into a variable that I've renamed test data just to make it a little bit more clear. The next step here is looking in our process environment for a variable called npm underscore package underscore description. And we're assigning that to a description variable. So this environment variable is automatically populated when npm, the package manager, which can also run scripts, runs one of its scripts. It populates environment variables for all of its data in its description. So what we're doing here is pulling from the environment something that comes from a package.json file, so the description field in a package.json file. And then we are passing that to the cryptography library in order to create a decipher instance. So what this means is that this description is our key to decrypt something. The next couple lines here, we're taking the first value from the test data, the first really, really long string, and we are decrypting that with that key that we got out of our environment. Next few lines here, we're creating a new module with the module.constructor method. Modules are modules in Node.js land. They're individual units of code and logic. You can ignore the paths. That's a Node.js thingy. We're compiling the text that we have decrypted into or as the contents of our module. So what this means is that first test data, that line there, is a JavaScript file that is being decrypted and loaded up as a new module. And then what we're exporting from that module is the second value of our test data. So that second really, really large string. So these end up being our payloads B and C. So now this is an important part here, because this is the key to actually going any further with this analysis. What we have to do right now is figure out where this key comes from. And I was doing a lot of this research on my own because it's fun and I like doing stuff like that. I'm not going to be brute forcing a massive, massive range of possible keys just because that's going to take too long and I don't have the hardware for it. So what we need to do is find good package.json files. This is an example package.json file, which is just from a completely unrelated package. Just happened to be something I was using during the research. And this is what scripts look like as they're defined in package.json. They just have a name and then essentially something you run on the command line. Now this is what we are looking for, or this is what is being run, and this is the structure, the package.json is the structure that all the data in the environment gets populated with. So we're looking for a package.json that has a description that successfully decrypts that first value in the test data. So where we're at so far, we have a script that decrypts and compiles a new JavaScript module. The key for the decryption comes from a package.json description somewhere. The encrypted JavaScript from there comes from test data, and the compiled module exports the second value from test data. So what this means is that this script will only serve its purpose if the code runs from an npm script in a directory that has a package.json that has a description value that successfully decrypts the test data. So what this means for us is that we just need to start trolling through package.json files. Now, anyone know about package.json files? Where would you find the biggest repository of package.json files? It would be in the npm registry itself. And luckily, when we wanted to go through all the packages there, we could just use an npm package called all the packages. Because there is literally something for everything on npm. And the funny part of this is that it, of course, depended on event stream. So as you're going through this, you just have to accept you are already screwed, and a lot of people are already screwed with something like this. So the strategy here was to iterate through every single possible package that existed in the npm registry, try to decrypt test data, the first value in our test data, Since we know that it's supposed to be JavaScript, and we also know that different keys can successfully decrypt data, it's just not going to get you the right data, we're going to take that decrypted data with the key that we have and then run it through a JavaScript parser to make sure that we're dealing with valid JavaScript, so we don't have to do it by hand, and then if successful, we have a winner. Now this is this was a long shot. This was all I was gonna do. If it didn't work, then I just was gonna have to deal with it because it's hard to just figure out what keys for random encrypted data are. That's supposed to be the way it is. So I'm not getting an updated here. There we go. So what we see right here is in just under a couple minutes, that was actually 20 seconds. To go through the entire NPM registry was a little under a couple minutes. We find a key that actually successfully decrypts this data and produces JavaScript. The description we were looking for was a secure Bitcoin wallet. So some package out there with a description with a value of a secure Bitcoin wallet was being targeted. This ended up being Copay, the secure Bitcoin wallet. So payload B. This is what injects, this is what gets run when we find out that we are running within the project that we want to be running in, and then injects payload C. Payload B, we can now decrypt because we have the key, and we're not going to go through every single line, but we're going to focus on a couple. So this particular line right here is testing the arguments that are being used to run this script, and if they do not match a particular regular expression, then we are going to bail. So what this means further is that we are more isolating the effect of this malicious code to a very, very specific environment. The way NPM scripts run, you type in npm space run dash script space and then the script you are trying to run. So our arguments here, the first argument is npm, the first element in argv is npm, second index 1 is run script, third index 2 is the script dash name, or the script name. And the regular expression we're looking for right now is something that includes build and then a literal colon and then anything and then a dash release. Now, because Copay is luckily open source, we can actually find out specifically what it was targeting. And the regular expression would match these scripts in the Copay's package.json. Anyone familiar with Cordova or PhoneGap? It's used to be very, very popular. It was one of the original ways of using web technology on mobile and native environments. So we'd use HTML, CSS, and JavaScript, package it up into a web view, and then you could deploy on app stores or iOS or whatever else. So this build step, build iOS release, build Android-release, build desktop-release. They were building HTML, JavaScript, and CSS into a native application, and that is what the application was. So payload B also had this line in it right here. This is a deep dependency, legitimate dependency of Copay --. And this is not a malicious file, but the payload B used this file because the developers knew that this file was being loaded in the context they wanted to be loaded in when the application was actually running. And what they did was inject the next payload into that file so that when that file was loaded in the application, their malicious code would run. So to recap here, payload B doesn't do anything unless it is run in Copay's build stage. It decrypts payload C, just like payload B, grabs the same key because the package and project is the same. It injects payload C into a file used in Copay's mobile application, and payload C is then executed in the mobile application itself on the user's mobile device. Payload C, the final payload. It looks like this, and we're actually not going to go through it because this is the final payload. And as a lot of us know, the final payloads are actually the least exciting of research like this, because this is just what the attacker wanted to do at the start and needed to figure out a way into the system in order to get it to actually run. It's a lot of web code. It's document.local storage, passing things with global variables. Essentially, what it did
harvested private keys. It's targeted wallets with a certain amount of Bitcoin or Bitcoin Cash, passed a lot of this data onto a third-party server. So where does this leave us now? This is not a Node or NPM specific problem. This is a problem with any sort of open source registry of code that you install any which way. The problem here is that JavaScript and NPM are incredibly popular, so we see things like this faster and we see more of it. But this is a problem that also exists in other open source ecosystems, and it's something that we're probably not going to see any shortage of. So the good news here is that once the issue was brought to light, the community responded very, very rapidly. Of course, the payload had already been in the wild for a month and a half, but that's a whole different issue, because as soon as people found it, they were very, very motivated to fix it. They developed tools that would analyze your system to determine whether or not you had any affected packages. Obviously, NPM took down the malicious package, issued security warnings. The community responded very, very rapidly. The bad news is that it's still happened multiple times since and doesn't really show any slowing down. This happened actually just a few months ago. This was another cryptocurrency application that was exploited, and this was exploited via another package, Electron-native-notify. Electron is the more modern version of Cordova. It's not developed by the same Cordova people, but it's the same sort of spirit. It's using web technology in order to produce native applications. So things like Visual Studio Code, Slack, Skype, those all use Electron. So this was targeting one of a plugin for Electron that allowed you to issue native notifications, and of course was used to steal Bitcoin, because that's what people do. Somewhat recently, last week, there was some analysis done on the NPM ecosystem, and it found that you could just exploit 20 people and take over essentially half of all NPM packages and projects. And this is a dependency system that has grown in a suboptimal way, and it is powering a massive, massive portion of our technology. Now, this could have been much, much worse. Luckily for us, real people, this malicious code very, very specifically targeted a specific system and a specific application. Now, I have to imagine that the person who went through the effort to actually do this, once they found out what they had, probably regretted that they only targeted Copay, because this was used by virtually everyone. There's millions upon millions of developers that were downloading this daily, and you could use something like Visual Studio Code and also have this problem, so you don't even need to be a Node.js developer or use NPM at all to have potentially been affected. This package was also used by Azure CLI. Azure is Microsoft's cloud offering, so you can also imagine the types of people who might be using the command line interface for a cloud offering like that. Internal to Microsoft, certainly, and very, very highly privileged developers all around the world. It was a massive, massive widespread problem. And this is probably going to get a lot worse. To be honest, this is not something that is going to easily go away. It requires us to reevaluate the way our systems are working. And unfortunately, for things like Ruby, Python, Node, and all existing stuff that is already very, very popular, a lot of these decisions involve backwards incompatibility and changes that will push the state of security forward, but are going to alienate a lot of your fans. And it becomes a marketing and cost versus value decision. And I think a lot of us probably know where security sits in most people's cost versus value justifications. Now, the developer of a node has actually shown interest in this particular problem. Ryan Dahl created Node a little over 10 years ago now, is no longer associated with maintaining the project, has not been for several years, but has started developing and showcasing a spiritual successor to Node called Dino, which is an experiment to elevate some of the problems in the Node.js environment so that we can better handle problems like this and a lot of other problems. And one of the things that it does well is isolate access to privileged APIs so that you have to explicitly allow them. I mean, same things like what we do on our mobile phone. You don't want Facebook to use GPS because you're a normal, sane person. You can disallow Facebook from using GPS because if you don't, they will do it because they're horrible people. Sorry for all Facebook developers and anyone who views this stream. You're probably a good person. But this is something that we don't have in a lot of our development environments, and we don't have in Node. And adding this sort of feature and having this module isolation and sandboxing and compartmentalization inevitably involves a lot of backwards incompatibility problems, and is something that's going to be very hard to wedge into the existing Node ecosystem. So what can you do personally to address this? You're all sane people. I love security audiences because a lot of this stuff isn't actually all that new to you. But worry about your dependencies. Now, when I talk to JavaScript people, they're like, what? This is all free. NPM install everything. But no, dependencies come with risk. Think twice before adding dependencies. Make sure you're locking your dependency versions so you don't get surprised when things change from underneath you. You do need to audit when things change. You need to make sure those changes are acceptable. When in doubt, don't add it. This, of course, involves, is something that you should apply to open source development for server-side applications, but also for websites. All those script tags you see that loads megabytes and megabytes of JavaScript and slows down your connections and computer. Only add those if you really need to, because all of this stuff is risk, and risk is okay if the value is greater than the potential downsides. But a lot of times we don't actually make that determination. We just throw things in and see where it takes us. So gamble when the cost is low and the value is high. Thank you very much.
Is the audience mic working? Thank you, Jarrod. If you have questions, we have about time for 2 or 3 good questions, or possibly one extremely compelling one. If you want to ask a question, please come to the microphone. If you are leaving the room, please leave through the doors at the rear. And I'll have tips for you if you're sticking around for the next talk. So any questions, please use the mic.
So you talked a little bit about the plans to make the language itself more resistant to this. Are there things that you want to see either NPM or GitHub or the other package systems adopt in order to make this harder to do?
Yes, but there are also problems with what I would like that I would hesitate to recommend. One of the serious problems that does exist is the disconnection between the original source code and the distributable. So a lot of people, of course, host code on GitHub, but then publish whatever to NPM. There's no actual link or assertion that what exists in a repository it ends up being what exists in the NPM registry. So like this example is a good one because what existed in NPM never actually existed in GitHub. So you had to actually get the distributable and dig through the distributable to figure out what was actually in it. Tying an open source code repository directly to its distributable will allow us a little bit more of a breadcrumb trail to figure out what's going on. But that does potentially consolidate a lot of power in a particular company like GitHub if they start to control more of the distributables, which is what they're doing now. So it's good for some things. Don't know how it's going to play out in the long term, though.
So the description is non-human readable key, and why isn't that being detected? And also, when you decrypted checking every package, did you run a linter to see if the description was a non-human readable key?
So the description actually was human readable. It was the string a secure Bitcoin wallet. So it was using that as the key to decrypt. It was using that as the key to decrypt its payload.
So Node could just put some formatting on its descriptions that would interrupt a key format, theoretically.
Can you repeat that a different way?
Node could. the
Is this
node
a- is this a-
system
a
could have
proposal?
Formatting around the description that would interrupt key formats. I think it could.
Yeah, I don't think there's nothing really special about taking the description out of this. This was just it could have been any value in that. It could have been something else specific to the project. It could have been something local to the file system. There was nothing really specific or special about that key. It was just I guess probably the first and easiest way to do that.
Yeah, I think it could be solved simpler than you guys think.
So it seemed like part of the key to this attack was the obfuscation, right? The multiple layers of obfuscation that they put in place. Given that these are kind of open source projects, is that something like a method that we could attack this from, right? Like not allowing that level of obfuscation in code?
So there are companies that do audit dependencies, and one of the things that they do is look for signs of obvious obfuscation. So strings that are hexadecimal values. The problem there is similar to the first question I answered, is that there's a disconnect between where the source code lies and who ingests the distributable artifact. So there's no actual connection there. So even though source code does exist in GitHub and is open, it doesn't mean that I can't develop something completely arbitrary and then publish that as the next version in something in NPM. As long as I have access to that repository in NPM and I'm an author in NPM, then I can publish anything. It doesn't need to be connected at all to what exists in GitHub. So having some sort of connection there is important, but that is something that I don't foresee happening in the near future, because companies playing well with other companies, who knows? Sometimes that works, sometimes it doesn't.
Are you familiar with Npm Audit and
Yep.
the degree to which it might remediate? So I get what you're saying about the disconnect between the packaging and the distribution, and it sounds like it's just kind of blacklisting things. So I don't know to the extent it would have even caught something like this currently. Does that make sense?
So NPM Audit is a great way to identify whether or not you have any, for people who don't know, NPM Audit is another command that can be run in the NPM package manager that will check your dependencies against any known security vulnerabilities or any security issues. And then give you a list of packages, severity, and can potentially fix some of those for you. The problem with that, though, is, of course, they only detect what they know, and there is a lot of noise there. Just like with a lot of linters that are too aggressive, as soon as you get a whole bunch of warnings that you know aren't actually that important, then you're just going to ignore everything. And the fact is, when you're just blanket auditing all of the dependencies in a project, you're going to come up with some security vulnerabilities, but some of them just might not be that big of a deal. Like there are a lot of security vulnerabilities that just won't actually cause you a problem ever, because you're never running the code that has a vulnerability in a scenario where the vulnerability can manifest. So when you run into audits like that and you see a lot of things like that, then it becomes very, very easy to just ignore everything.
All right, another round for Jarrod. Thank you very much.